Hello everyone, this is our first lecture for Chapter 6, An Introduction to Probability. Here are the learning objectives for Chapter 6. This is what we are going to go over, and this is what you will need to know for the next proctored exam. Think of these learning objectives as your roadmap through the chapter and your study guide for the exam. Take a minute, hit the pause button, and read through these. In this lecture video, we will define probability and introduce some of the terminology needed to understand probability. So far, we have discussed the collecting, organizing, and summarizing of data, or descriptive statistics. We are almost ready for inferential statistics, but before we can proceed with analyzing data, we introduce probability, which is the basis for inferential statistics. Why? Well, we think of the probability of an outcome as the likelihood of observing that outcome. If something has a high likelihood of happening, it has a high probability, close to 1. If something has a low probability of happening, it has a low probability, close to 0. For example, in rolling a single die, it is unlikely that we would roll 5 straight 6s, so this result has a low probability. In fact, the actual probability of rolling 5 straight 6s is 0.0001286. So if we were playing a game that involved throwing a single die, and one of the players threw 5 6s in a row, we would consider the player to be really lucky, or a cheater, because it is such an unusual occurrence. Statisticians use probability in the same way. If something happens that has a low probability, we investigate to find out why it happened. One goal of this course is to learn how probabilities can be used to identify unusual events. An unusual event is an event that has a low probability of happening. Typically, an event with a probability less than 5% is considered unusual, but this cutoff point is not set in stone. The researcher and the context of the problem determine the probability that separates unusual events from not so unusual events. For example, suppose the probability of being wrongly accused of a capital crime punishable by death is 3%. The probability is too high in light of the consequence, death for the wrongly convicted, so the event is not unusual or unlikely enough. We would want this probability to be as close to 0 as possible. Now, suppose that you're planning a picnic on a day for which there is a 3% chance of rain. In this context, you would consider rain an unusual or unlikely event and proceed with the picnic plans. The point is this: selecting a probability that separates unusual events from not so unusual events is subjective and depends on the situation. Statisticians typically use cutoff points of 1%, 5%, and 10%. For many circumstances, any event that occurs with probability of 5% or less will be considered unusual. Probability is part of everyday life. It is the key to assessing and understanding the risks involved in any decision-making process. It guides our expectations. Probability lies at the heart of statistical inference. Whenever we generalize from a sample to a population, we do so with a probability statement. Probability is a measure of the likelihood of a random event or chance behavior expressed in numerical terms as a fraction, decimal, or percent. Probability describes the long-term proportion of a certain outcome in situations with short-term uncertainty. The long-term predictability of chance behavior is best understood through a simple experiment. So before we start getting into the specifics of probability, I would like for you to do a simple probability experiment. Using a penny, flip the penny 10 times and record whether it lands on heads or tails. Then find the probability of landing on heads by calculating the relative frequency of heads, or the number of times your penny landed on heads, divided by the number of times you flipped the penny, or divided by 10. You will notice that your probability is somewhere between 0 and 1. Now flip the penny 30 times and record whether it lands on heads or tails, and find this probability. Is your probability closer to 0.5 or 50%? You might notice that in the short term, or fewer flips of the coin, the observed proportion of heads is different and unpredictable for each individual trial or coin flip. As the number of flips of the coin increases, however, the observed proportion gets closer to 0.5. This is the basic premise of probability. Probability deals with experiments that produce random, short-term results or outcomes, but reveal long-term predictability. If we look at the proportion of times an event has occurred over a long period of time, or over a large number of trials, we can be more certain of the likelihood of its occurrence. Here's another way to look at this. All of you have someone in your life that you know really well. You've known them for many years. Over the years, without realizing it, you've been collecting data about this person or people. I ask you, can you predict how this person or these people will react in certain situations? Most of you will answer, oh yes, I can totally envision how this person will react, or what they'll say, what they will do, and so on. Now imagine meeting someone for the first time and trying to predict how they are going to react or what they're going to say. More difficult, right? This is what makes meeting new people such an uncomfortable experience for some of us. We as humans like predictable outcomes, and our friends and family members usually provide that predictability for us. New people are unpredictable and make some of us feel uncomfortable. That is, until we collect enough information about them to start predicting how they will act. So chance behavior is unpredictable in the short run, but has a regular and predictable pattern in the long run. The probability of a coin flip landing on heads is 1/2, or 0.5, or 50%, because the more times we flip the coin, the proportion of coin tosses landing on heads gets closer to 0.5. This is referred to the law of large numbers. The law of large numbers states that as the number of repetitions of a probability experiment increases, the proportion with which a certain outcome is observed gets closer to the probability of the outcome. The coin flip activity illustrates the law of large numbers. For a few flips of the coin, the proportion of heads fluctuates wildly around 0.5. But as the number of flips increases, the proportion of heads settles down near 0.5. In probability, an experiment is any process with uncertain results that can be repeated. The result of a single trial of the experiment is unknown ahead of time. However, the results of the experiment over many trials produce regular patterns that allow us to predict with remarkable accuracy. For example, an insurance company cannot know ahead of time whether a particular 16-year-old driver will be involved in an accident over the course of a year. However, based on historical records, the company can be fairly certain that about 3 out of every 10 16-year-old male drivers will be involved in a traffic accident during the course of a year. So of the 816,000 16-year-old drivers, or 816,000 repetitions of the experiment, the insurance company is fairly confident that about 30%, or 244,800 of the drivers, will be involved in an accident. This prediction forms the basis for establishing insurance rates for any particular 16-year-old male driver. So now let's get into the specifics of probability. The range of values for any probability statement can be from 0 to 1. The probability of any event E must be greater than or equal to 0 and less than or equal to 1. Probabilities range between 0 and 1 inclusively, like any proportion. Probabilities less than 0 or greater than 1 are not possible. For example, probabilities such as 1.32 or negative 0.3 are not possible. Or sometimes you might hear someone say that they gave some activity 110%. This is impossible. If an event is impossible or will never happen, the probability of the event is 0. The probability of an impossible event is 0. For example, the probability of snow today in the San Fernando Valley is equal to 0. If an event is a certainty or will absolutely happen, the probability of the event is 1. The probability of a sure thing is 1. So for example, the probability that your statistics professor is female is equal to 1. The closer a probability is to 1, the more likely the event will occur. The closer a probability is to 0, the less likely the event will occur. I mentioned probability experiments earlier. These are situations where chance affects the result of an experiment. A probability experiment could consist of one or many trials where each trial produces one outcome. It could be a very simple experiment, like our coin toss, or it could be much more complex, involving many trials and several series of outcomes. All probability experiments have 3 things in common. 1, the experiment must have more than one possible outcome. 2, each possible outcome can be specified in advance. And 3, the outcome of the experiment is due to chance. Examples of probability experiments include one die roll to see if the number 4 comes up. Probability is 1 out of 6 or 0.167. A coin toss to see if it lands on tails. Probability is 1 out of 2 or 0.5. A card pick out of a deck to see if it's a queen of hearts. Probability is 1 out of 52 or 0.019. A coin tossed 4 times to see how many times it lands on heads. Probability is 1 out of 2 to the 4th power, or 0.5 to the 4th power. These are not probability experiments. A football player runs for a touchdown. A person buys a raffle ticket, or your school club sponsors a Las Vegas night to raise money for charity. We now introduce some terminology to better understand probability. A trial is defined as a single performance of a probability experiment. In the die roll experiment, 2 slides ago, one roll of the die represents one trial. In the first coin toss experiment, one toss of the coin represents one trial. In the card pick experiment, one pick of the card represents one trial. In the second coin toss experiment, the series of 4 tosses represents one trial. An outcome is the result of one trial of a probability experiment. In the die roll experiment, the result of that roll of the die represents the outcome. There are 6 possible outcomes, 1 through 6. In the first coin toss experiment, the result of that toss represents the outcome. There are 2 possible outcomes, heads or tails. In the card pick experiment, the result of that card pick represents the outcome. There are 52 possible outcomes, 52 cards in the deck. In the second coin toss experiment, the result of one series of tosses represents the outcome of that trial. There are 16 possible outcomes. The sample space is a list of all possible outcomes of a probability experiment. The sample space of a probability experiment is the collection of all possible outcomes. The sum of the probabilities of all possible outcomes in the sample space must be equal to 1. For example, in the coin toss activity, the sample space is heads and tails. The probability for each outcome is 0.5. Probability of landing on heads is 0.5, and probability of landing on tails is 0.5. The sum of these 2 probabilities, 0.5 plus 0.5, is equal to 1. The probability of one outcome, or x, is calculated as x divided by the total outcomes in the sample space. One last definition for this video lecture is the complements of events. The complement of any event is all outcomes that are not that event. The complement of event A is A prime, representing the probability of A not occurring. So the probability of A prime, or A not occurring, is equal to 1 minus the probability of A, or the probability of A occurring. In the next video, we will discuss different types of probabilities.